Hello. In this video we're going to take a look at the finite potential well. We've looked previously at the infinite potential well. Now we're going to bring that potential down to a finite value. So the potential is as follows. So 0 within a region of x as before, and V0 otherwise, where V0 is no longer infinity. This time we've set it up so that the well is symmetric about 0. It just makes the math slightly simpler to work with. Let's draw it. So it's symmetric about 0, and it has height V0, and this is 0 down here. Now let's try to guess what the solutions look like. So down at the bottom of the well, we'll have some bound state down here, just like we did in the infinite potential well. I'm going to sketch it in this slightly dodgy way of drawing the wave functions onto the potential plot at a snapshot in time. So before, the lowest energy state looked like this. In fact, let's draw that in a different colour. So the solution to the infinite potential well looked like this. We're going to have something like that, but there's no longer a requirement that the wave function vanishes at this point, because remember, the wave function only has to vanish in regions where the potential is infinity. So using this as motivation, we can guess that the lowest energy state might look something like this. That is, it takes the form of standing waves within the well, but it doesn't need to vanish at the edge of the well, and outside of the well, it isn't 0, it's exponentially decreasing. Remember our solutions both to the infinite potential well here, and also to our scattering from an infinitely long but finite height potential step. So that's the lowest energy state. We might guess, similarly, that if we have another bound state up here, it might look something like this, where again, this is a snapshot in time of the real part of the wave function psi, and this will again come off to 0 like this. And we might have higher energy bound states in the well. There's no requirement for there to be an infinite number of bound states, which there was in the infinite potential well. We can only fit some number in before the energy of the states is higher than that of the well. And when we do that, we then expect the solutions to be plane waves. There will be some kind of boundary condition going on here because of the edge of the well. But in general, we'll have a continuum of different plane wave states above the well. So there's an infinite number of these. There's only a finite number of states trapped within the well. Taking a look at the forms in the different regions, we can guess that we'll have standing waves in here. Remember, our general types of wave solution are either plane waves, types of solution for regions with constant potential are either plane waves, which we have up here. They're standing waves, a form of plane wave, but where we have equal contributions from left and right going waves, which we expect within the well. And they can be evanescent waves, exponentially increasing or decreasing. And note that over here, our physical guess was that we have exponentially increasing solutions in this region and a decreasing solution over here. Okay, so let's write down the forms of those wave functions and substitute in the boundary conditions on the next board. Sorry, didn't erase it. One more go. Sorry, the board's playing up. Oh, sorry, I must have it set to change my clothes. Right, oh, I know, yeah, okay, got it. Got it, okay. All right, so wave functions in the different regions. It depends on whether the energy is greater than or less than V0. If it's greater than V0, we're just back to plane wave solutions in all three regions, and we're solving exactly the same problem as the scattering over the top of a potential barrier, which you've seen in a previous video. So let's only consider the bound states which lie with energy less than V0. In that case, we have the following results in different regions. So let's call it region 1. X is to the left of the well, so less than minus L over 2. We have phi 1 equals unknown coefficient A, e to the kappa x. It must be exponentially increasing in order to die off at x equals minus infinity, rather than blow up. Similarly, in region 3, that is, x is greater than L over 2. In region 3, we must have the form unknown constant d, e to the minus kappa x, where kappa is the same kappa as appears in region 1 because the potentials are the same, both equal to V0. That is, both of these, when substituted into the time-independent Schrödinger equation, give the form minus h bar squared kappa squared over 2m plus v naught, and this ensures that we can have real kappa for E is less than v naught, which is what we'd like. In region 2, we're looking for standing wave solutions, which is convenient to write in terms of causes and sines, but we could always write it in terms of complex exponentials. And in region 2, we solve a different time-independent Schrödinger equation because the potential is 0 in that region, and we have E equals h bar squared k squared over 2m. Okay, we can substitute in, so we're going to substitute these into the boundary conditions as usual, but actually there's an easier way to do it in this case, physically motivating it based on our guesses of what the wave functions will look like. Let's just redraw that quickly down at the bottom here. So, loosely drawn, the real parts of the wave functions. We can see that this is region 1 over here, 2 inside the well, 3 over here. So we can see there's going to be an odd-even effect. Whenever n, so starting with the ground state n equals 1, where the ground state is the energy eigenstate which has the lowest energy eigenvalue, this state is symmetric about 0, although I've drawn it rather badly. It's an even function. That's also going to be true for any other odd states which appear. So state 3, which would have, so state 2 has 1 node, state 3 will have 2 nodes at 1/3 and 2/3, and so on, or approximately in those areas. And all the odd n solutions will be even functions, and all the even n solutions, like this one, will be odd functions. And so in particular, we can see the following. So when n is an odd number, we have both the exponentials coming up like this towards the well, and so what we're saying is that A must equal D. You can see from symmetry that their magnitudes are going to be the same, because there's not going to be any mismatch here. The potentials are symmetric. So the magnitudes are the same, and in fact the signs must also be the same. At the same time, within the well, we also want a symmetric function. Cos is symmetric, but sine is not, and so we must have C equals 0. We could have deduced this from applying the boundary conditions here and here, but this is a quick way to do it. Similarly, when n is even, we have the exponential coming up here, but it's doing effectively the opposite here. It's still a negative exponential in this region, but it's going to have a negative coefficient, and so we must have that A equals minus D. And since we're looking for odd functions now, the cos terms must disappear, and we must have B equals 0. Okay, so we're doing pretty well without even having to do any algebra. Let's clear off the board again, and then we'll apply our general boundary conditions to get further constraints on these solutions. Right here. Okay, one more go. All right, well, I'm back to normal. Sorted. Okay, so the two types of solution we have for odd and even n are as follows. For n odd, phi takes this form, a e to the kappa x in the region 1, b cos kx in region 2, a e to the minus kappa x in region 3, and when n is even, we have a e to the kappa x, c sine kx, and minus a e to the minus kappa x. Okay, so we had 4 unknowns, a, b, c, and d, and 4 boundary conditions, 2 at each of the joining points. We've used 2 of our boundary conditions implicitly in writing these forms, so we need 2 equations left. So we can take, for example, the condition at the left end of the well, and we can write these 2 following boundary conditions. First, the wave function is continuous. Second, the first derivative of the wave function is continuous. And substituting these into the expressions, we find these constraints. First, a e to the minus kappa L over 2 is equal to b cos kL over 2 for n odd, or minus c sine kL over 2 for n even. And for the first derivative expression, we have either bk sine kL over 2 or ck cos kL over 2, depending on whether it's odd or even. Combining each of the expressions, so remember this one goes with this one goes with this one, we get we'll divide one by the other in each case, and we'll get the following constraint on kappa and k. For n odd, we find that kappa is equal to k tan kl over 2, and for n even, kappa is minus k cot kl over 2, where cot is 1 over tan. So these constraints are the best we can do. Remember, in the infinite potential well, we had a much nicer constraint, which was that k times L had to be some integer multiple of pi. But now the best we can do is find a matching condition. So you can think of it as we stated that we must have standing waves inside the well, but we didn't say what their wavelength had to be. And in the infinite well, we know the wavelength is dictated by the fact that we need the wave function to vanish at the edges of the well, but that's no longer a constraint. So the wave can stretch so that its wavelength is not an exact match to the well. And in fact, it can't be, because the wave function has to have some finite amplitude at the edge of the well in order to exponentially decrease away from the well. So this is the best we can do. These equations are what are called transcendental equations, meaning it's impossible to solve them analytically. The best we can do, you can solve them numerically, but we can actually seek a graphical solution. So let's take a look at that on the next board. Let's just take a look at the odd solution. And we can substitute in the expressions for E and V0 into here, remembering that they're defined as follows. And so we can rewrite these like this. Substituting them into the expression, we find this. Squaring both sides, we have, and we can add the E over to the other side. Note that 1 plus tan squared is sec squared, which is 1 over cos squared, and rearranging this gives. This isn't the only way to do this, to simplify the expression in order to plot it. This is just one that happens to work quite nicely, but you can find your own. And so we can plot both sides of this on the same axis. So that is, the axes are the energy E along here, and here it's going to be a function of that energy. The first function is just E itself, the left-hand side, so it's just a 45-degree line. The second function is this. It's a bit hard to plot, but we know what cos looks like, cos of E, so we know what cos squared looks like. And then we take that and then we stretch it according to the fact that we're not plotting E, but it's not E inside the cos, but square root of E. And we also scale it so that its first zero lies at square root me over 2 times L over h bar is equal to pi over 2. Okay, so what this tells us, though, is one important thing, which is that there is certainly a solution. Okay, because E always increases from 0. This cos squared of square root of E always starts at V0 here and it decreases, and so they must intersect. And so what this tells us is that for any arbitrarily weak potential V0, there must be at least one bound state in the well. There is always one bound state in a finite potential well at any depth whatsoever, at least one. And in fact, that if there is one, it must have n odd. It's the ground state of the problem, of course, the ground state being the lowest energy eigenstate. So if we did the same for n even, we would, let me get rid of this and redo this bit for n even quickly. So exactly the same, but with a sine instead of a cos. Here's what I made earlier. And it may have a solution, an intercept, as shown here by the pink curve, but it may not, as shown here by the blue curve. It just depends on the particular values of V0, for example, and L could also cause that to change. Okay, thank you for your time.